All right, I want to look at how to find the eigenvectors that go with a given eigenvalue. So recall that the eigenvectors that go with a given eigenvalue, they form a subspace of Rn. This subspace is called the eigenspace of lambda. And when we're asked to find the eigenvectors that go with lambda, it's good to just give a basis of that eigenspace. So I want to do some examples of this. First up, I want to do example 401 just by using the definition of eigenvalue and eigenvector. And then after we do that, we'll look at this down here, which is a more streamlined way of doing it. But I don't want to just launch straight into doing this because doing it from the definition is going to show us where this stuff comes from. All right, so if this is my matrix, I'm going to let x, y, z be my eigenvector. Or I guess I should say be an eigenvector. So if we multiply that by this, it's the same as taking x, y, z and multiplying it by the eigenvalue, which is -3. So what I'm going to do here is multiply this out and multiply this out. Multiplying this out over here is going to give me 5x plus 8y plus 16z. And over here, this is going to give me -3x. Then the second row is going to give me 4x plus y plus 8z. And this is -3y. I get -4x minus 4y minus 11z equals -3z. Okay, so I've got this system now. So what I want to do now is take each one of these 3x, 3y, 3z's, and I'm going to add these onto both sides. So this is going to get added on and affect this. I'll add this onto both sides. It'll affect this guy. And same thing here. So by moving this to the other side, the system becomes 8x plus 8y plus 16z equals 0. The next one is 4x plus 4y plus 8z equals 0. And the last one is 4x minus 4y minus 8z equals 0. And notice something interesting happened here. Typically when you do this, this is going to be a system where one of the rows, at least one of the rows, is a linear combination of the others. But notice on this one, all these rows are multiples of each other. So let's take this and we're going to put it back into a matrix. 8, 8, 16, 0, 4, 4, 8, 0, -4, -4, -8, 0. And we're going to row reduce this thing. You know what we're looking for solutions to this. Solutions are going to be very, x, y, z triples that satisfy this. So the solutions are going to be our eigenvectors. Now this thing we can actually row reduce pretty easily. Since all the rows are multiples of each other, that top row you could divide by 8 and get 1, 1, 1, 2, 0. And the next two rows you can subtract multiples of the top row and just get all zeros here. All right, so something interesting happens. If I rewrite this as a solution, x, y, z, y and z are both free variables. So notice that gives me, the top line gives me x is equal to minus y minus 2z. Y is just y, and z is just z. So I can rewrite this for my vector x, y, z. I'll come over here and sort of drawing some boxes. Basically, we've got that plus this. So this is equal to y times negative 1, 1, 0 plus z times negative 2, 0, 1. So the basis of the eigenspace is all the vectors that are linear combinations. Well, actually, I don't need to say that. The basis of the eigenspace is those two vectors right there. Okay, now I want to play with this a bit. So let's go to Desmos, not Desmos, Octave. Now I think I've already got this matrix in as M. Let's see. Yeah, that's my matrix M, and according to this, my two this basis of eigenvectors, one of them, let's call these vectors. I'm just going to give them names in Octave here. I'm going to call them vector A and vector B. So A is going to be negative 1, 1, 0, and B is negative 2, 0, 1. All right, so if I take M and multiply it by A, well, first up, let me do this. Here was A. If I take M and multiply it by A, since the eigenvalue we're looking for here was negative 3, when I multiply this out, it should give me this vector here, but multiply by negative 3. And sure enough, it does. It'll do the same thing for B, except I forgot my semicolons. Okay, so there's B, and if I multiply M times B, it should give me 6, 0, negative 3. Sure enough, it does, because both of those are eigenvectors that go with the eigenvalue negative 3. And this works not only for A and B, but it works for any linear combination of them. So I'm going to pick a random number, say 6. 6 times A minus 17 times B. I'm just picking those numbers out of anywhere. If this were a normal class, I would ask people to give me random numbers. Let's see, so that gives us this. Now, if I take the matrix M and multiply it by this should give me 3 times that. So, or I'm sorry, negative 3 times that. So my middle number is going to be negative 18, and my bottom number is going to be positive 51. And my top number is negative 84, which I couldn't do in my head very quickly. But anyway, this is the eigenvectors that go with negative 3 here consist of all the linear combinations of these two guys here. All right, now that was doing this from just the definition. This is a more streamlined way of doing this. To find the eigenvectors that go with the given eigenvalue, you form this matrix here. Now this matrix is gotten by taking A and subtracting the eigenvalue off of the main diagonal. And if you look at it, that's exactly what we have right here. That's starting with this and subtracting the eigenvalue negative 3 off of the main diagonal. So this turned into 8, 4, and negative 8. So that's exactly what we did up above. Then row reduce it and find the general solution. So we'll do some more examples of this in the next video.